Here's the practical answer. Do not force every tool inside Codex. Use Codex as the core worker, OpenCodex as an isolated reviewer, and CC Switch only when routing, logs, costs, and rollback are inspectable. This is PyPy AI Everyday Lab. Practical AI workflows with clear limits. So, today we are mapping out the final architecture for your multimodal workspace.
Right, yeah. Which, like you just laid out, means Codex stays as your core worker, OpenCodex is your isolated reviewer, and CC Switch is just, an outer switchboard.
Exactly. And because we have all felt the pain of a completely broken dev environment, we're also going to preview a fixed failure right now. So for example, if you run into a model not found error or a wrong provider route, you can fix it by reading back the active route, selecting a confirmed model, and then running exactly one read-only request before allowing any real write access.
Yeah, that approach is just fundamental. I mean, it shifts your mindset from blind trial and error to actually establishing verifiable boundaries. You really have to secure the perimeter before you let an automated system touch your critical files.
Right. And that is really the core mission of our deep dive today. We are navigating the completely chaotic world of multi-model workflows. Like, imagine you are staring at your terminal right now. You're trying to chain different AI model vendors around Codex.
Oh, yeah, the classic setup.
Yeah, you want to plug in Anthropic for some nuanced reasoning, DeepSeek for a specific coding task, maybe Google's Gemini, because you need a massive context window. So you wire it all up, you hit enter, and suddenly, nothing works.
Right. The terminal just bleeds red text.
Exactly, and you have absolutely no idea where the failure actually occurred.
It is an incredibly valid frustration. I mean, the underlying desire there is sound, right? Having access to a diverse model provider ecosystem is undeniably powerful. You inherently want the best model for the specific task.
Yeah, of course.
The breakdown really happens in the implementation because the current trend is, blindly stacking routers and translation layers on top of each other, and that just creates this incredibly fragile house of cards. When that stack collapses, your diagnostic visibility is literally zero.
I always think about it like plugging a power strip into another power strip, and then, plugging a third power strip into that one.
Yes, that is a great visual.
Like, it works for a minute. Plug in your monitors, your PC, maybe a space heater, but eventually a breaker trips. The lights go out, there might be a spark, and you were just standing in the dark holding a massive tangle of cables. You have no idea which specific connection caused the overload.
Right. You just know everything is broken. And let's take that metaphor deeper into the mechanics of API traffic. When you stack API proxies like those power strips, you are physically losing the diagnostic signal at every single network hop.
Wow. Every single hop.
Yeah. A proxy isn't just a pass-through. It terminates the connection from the client, reads the payload, creates a brand new connection to the next destination, and then repackages the payload. So if an error happens, say a timeout or a malformed header, the intermediate proxy often just swallows the original error code.
Oh, man. So it just spits out a generic 500 internal server error.
Exactly.
So you completely lose the paper trail. You don't know if the problem was the space heater or the second power strip or, the wall outlet itself.
Precisely. Which is why we really need to work backward today. Rather than building up from a mess of tools, we need to establish the ultimate conclusion of how this architecture should be constructed. The foundational rule we need to cement right now is this: do not chain everything inside Codex.
Okay, I want to break down our three main players based on that rule. First up, we have Codex itself. If we aren't chaining everything inside of it, what is its actual job?
Codex stays the main execution worker for your production work, and this requires a bit of discipline. If Codex is your environment of record, like the literal place where your actual source code is being modified, you have to let it do the heavy lifting natively.
So no third-party stuff inside it.
Right. The mistake developers make is trying to gut Codex and replace its internal routing mechanisms with third-party plugins. Just let the core worker be the core worker.
Core worker focused on the files.
Got it.
So player 2 in this stack is OpenCodex.
OpenCodex should be treated strictly as a separate reviewer or a second opinion. Think of it as a parallel lane on a highway. It is absolutely not something that you silently embed inside Codex.
Right, it exists alongside it, running its own processes.
Exactly.
And then player 3, which seems to cause the most polarized opinions, is CC Switch.
Yeah, CC Switch acts as an optional outer switchboard. And I really want to stress the word optional here. It should only be introduced into your workflow when you, the operator, can clearly inspect the active route, the model name, the exact financial cost, the error logs, and the rollback state.
So full visibility is required.
Absolutely. If a tool acts as an opaque black box, obscuring where your data is actually going, it simply does not belong in a professional stack.
I hear that, but let me push back a little bit. For the developer sitting at their keyboard at 2 in the morning, wrestling with API keys and endpoint URLs, wouldn't a unified master app just be easier?
I get that.
Like, why not just bundle all this routing and execution into one giant super tool?
Well, the appeal of a monolith is always strong at the beginning because it reduces upfront configuration. But in practice, monolithic setups lead to invisible layers. When you bundle everything into one super tool, you introduce severe protocol mismatches that are buried deep in the source code.
So debugging becomes basically impossible.
Right. Did the request fail inside Codex's file parser? Did it fail in the translation bridge? Was it the local proxy? The upstream provider itself? If they are all mashed into one executable, you cannot isolate the variable. Separation of concerns is really the only way to maintain a safe, reversible workflow.
You want to be able to unplug one single power strip, test it, and see if the lights come back on.
Exactly. You need modular observability, which naturally brings us to the question of what genuinely belongs inside Codex. Because if we are isolating Codex as our native worker, we need to understand how to configure it safely without resorting to hacks.
Right. And configuring the Codex native provider settings is definitely the safest, lowest complexity path you can take. Like, if Anthropic or DeepSeek or whoever supports a direct native integration, just use the native configuration.
Yeah, don't add a router just for the sake of having a router. Simplicity is always the most resilient architecture.
So true. And all of this native configuration happens in one specific file that truly matters, right? The config.toml file.
Yes, the config.toml file, located in the .codex directory. For those on Windows, that resides in your user profile folder, usually under C drive, users, your name, .codex, config.toml.
Let's open up that toml file conceptually. What are we actually writing in here? Because if we're keeping it minimal, every line really needs to justify its existence.
The parameters are highly specific. First, you have your provider settings. You define the model_provider and the model string. For example, if you are pointing to a custom organizational gateway, your model provider might be set to custom, and your model might be GPT 5.4 or whatever identifier that gateway expects.
Okay, and if we are using an OpenAI-compatible endpoint, say a local inference server or a third-party aggregator.
Then you define the base_URL. Instead of hitting the default OpenAI servers, you might point it to your company gateway.example/v1.
Now, what about the API key? Because I see developers hard-coding their production keys directly into their config files all the time, and it feels like a massive security risk.
Oh, hard-coding keys in a standard configuration file is a terrible practice, especially if you ever back up your dot files to a public GitHub repository.
Yeah, that's a nightmare waiting to happen.
Codex handles this securely, provided you configure it correctly. In your config file, you do not write the actual API key. You use the n_key setting to point to an environment variable.
So you would write something like env_key equals my custom API key.
Exactly.
But where does the actual secret string live? It has to be injected into the environment somehow.
Right. It should be securely stored in an auth.json file located right alongside the toml file inside that .codex folder. And here is the critical security mechanism. That auth.json file must have 600 permissions.
Okay, for the non-Linux natives listening, that means running commode 600 on the file, meaning only the current user account can read or write to it. No group access, no public access.
Yeah, and it goes deeper than just preventing another user on the same laptop from opening the file. Having strict 600 permissions prevents background daemons, rogue scripts, or overly aggressive telemetry tools from casually scraping your environment variables.
Oh, wow, that makes total sense. Protects your billing keys from being exposed. But there's another crucial detail in this config file that we need to highlight because it represents a massive shift in how these tools talk to each other. The source material calls it the protocol constraint.
Yes, this is perhaps the most significant architectural change in recent history. Codex has completely removed support for the old API format. If you write wire_AP equals chat in your config today, Codex will literally just crash on startup.
I've seen that crash. It just spits out a fatal error complaining about wire AP and refuses to boot.
Codex now exclusively uses the OpenAI responses API, so you must set wire_AP equals responses. This is not just a semantic naming change. It is a fundamental structural overhaul of the HTTP payload.
I want to pause here because this is where developers get incredibly confused. The audience knows what an API is, but why does changing a single string from chat to responses completely break the communication? What is happening under the hood?
Well, the old chat completions API was designed for chatbots. You send an array of messages and the model streams back text tokens. It's relatively simple. But the responses API is designed for autonomous agents.
That's more complex.
Vastly more complex. It handles tool calls, file diffs, and state management. Instead of just sending back raw text, the responses API streams structured JSON chunks that dictate precise file modifications. If your third-party gateway only speaks the old chat dialect, it physically cannot process the rich metadata Codex is trying to send.
Okay, let me try to extend my master chef analogy from earlier to explain this.
Go for it.
In my head, the config.tonpoll file is the instruction sheet you hand the chef before their shift, telling them which grocery store to go to. Changing the base URL is just changing the address on the sheet. But this protocol clash, it's like sending our English-speaking chef to a grocery store in Tokyo.
I like this.
Like, the address got him to the right building, but once he's inside, he can't read the labels on the ingredients. Codex natively speaks the responses API. That's English in this scenario. But if the custom endpoint only speaks the old chat completions dialect, Japanese, the chef leaves the store empty-handed. You can't just change the tom poll to fix a language barrier.
That is an excellent extension of the metaphor, and it brings us perfectly to the core problem. What do you do when the provider you desperately need to use doesn't natively speak the responses API? You cannot rewrite Codex's internal binary.
Right, and that is the exact void that OpenCodex was built to fill. But before we explain how it translates, we need to establish a strict framing rule based on the source material. We must not overclaim what OpenCodex is.
Yes, this misconception is everywhere on developer forums. Developers assume OpenCodex is a plugin. Let me be definitive. OpenCodex is not something silently embedded inside Codex. It does not alter the Codex binary.
So if it's not a plugin, what is its true identity?
You should view OpenCodex as a completely separate multi-provider coding agent or a distinct review lane. Functionally, it operates as an OpenAI-compatible router. It sits as an independent service on your local machine, typically binding to localhost on port 10100.
So it's a dedicated translator sitting between the chef and the grocery store.
Precisely. It exposes non-default models through an interface that Codex naturally understands.
Walk me through the actual mechanics of that translation, like what happens to the data?
Codex generates a payload using the responses API format. It fires that request to localhost 10100. OpenCodex intercepts it. It unpacks the JSON, reads the complex tool calls, and restructures that entire payload into the specific format the target provider requires. Yeah, then it waits for the response, translates the proprietary response back into the responses API format, and hands it back to Codex.
Here is where it gets really interesting and, frankly, a bit dangerous. If OpenCodex is acting as our separate reviewer, translating all these models, how do we physically keep it from stepping on Codex's toes?
They absolutely will collide unless you enforce strict workspace isolation.
Right. If they're both working on my local project, aren't they going to create a mess?
Yes, it will be catastrophic for your files. This is why the architecture mandates using OpenCodex in a separate Git work tree.
A Git work tree. I know a lot of developers who just use standard Git clone and Git checkout for everything. Explain why a work tree is necessary here.
Well, a standard Git checkout changes the files in your current working directory. You can only have one branch active at a time in that folder. A Git work tree allows you to check out multiple branches of the exact same repository into different physical folders on your hard drive simultaneously.
Okay, so they share the same underlying .git database, but the physical files are isolated.
Exactly. And this enables what we call the single writer rule. If Codex is operating in folder A, writing code, generating tests, you do not want another automated agent like OpenCodex simultaneously writing to those exact same files in folder A.
Let's talk about what happens at the byte level if you ignore that rule. What does that concurrency nightmare actually look like?
Imagine Codex is in the middle of streaming a massive file diff into app.py. It opens the file, locks it, and starts writing bytes. Meanwhile, OpenCodex, responding to a different query, tries to inject a function into the same app.py. Yeah.
Oh.
Depending on how your OS handles file locks, OpenCodex might force its way in, interleaving its bytes with Codex's bytes. You end up with a completely corrupted, abstract syntax tree.
You literally lose data. The file gets mangled beyond repair.
Yes. So you let Codex do the heavy lifting in the main folder. Then you point OpenCodex at the separate worktree folder. You can use OpenCodex to suggest sweeping architectural edits or act as a second opinion without any risk of it corrupting the active files.
That is brilliant. It gives you the power of multiple models without the chaos of multiple hands grabbing the same steering wheel. But this introduces a management problem. What if you want to orchestrate all these different profiles across multiple tools?
That complexity is exactly what drives developers to adopt third-party profile managers, which introduces our final architectural component, CC Switch.
Introduce CC Switch for the listener. What exactly is it doing?
CC Switch is a third-party profile manager equipped with a unified graphical user interface, a GUI. Crucially, it also includes an optional local proxy service.
The pros are obvious for anyone who hates command line configuration. Fast profile switching. You click a button in a nice UI, and you instantly swap from your official subscription to a pay-as-you-go API gateway.
Right, it provides centralized management. Instead of digging into multiple hidden folders to update environment files, you manage all provider credentials in one unified dashboard.
It is a massive convenience feature. But this is the deep dive. Convenience almost always comes with a hidden tax. We have to talk about the cons and the hidden dangers of wrapping your entire development stack in a third-party manager.
The drawbacks are severe if you don't understand the underlying proxy architecture. Let's break down the specific risks, starting with added protocol risk.
I really want to spend some time on this because I read about a specific issue in the source materials. The PRXY managed bug. It sounds like an absolute nightmare to debug. What exactly is happening there?
It is a textbook example of what happens when proxy middleware tries to be too clever. When you enable the CC Switch proxy takeover, it attempts to route all your CLI tool traffic through its own local proxy. To accomplish this without writing your actual API key into the local config file, CC Switch injects a literal placeholder string, which is PROXY_managed, into your tool settings.
Wait, so Codex boots up, reads the toml file, and thinks his actual API key is literally the word PROXY managed.
Yes. The intended architecture is that Codex sends the request to the CC Switch local proxy. The proxy's middleware inspects the header. It sees the PRXY managed string, strips it out, queries its internal database for your real API key, injects that real key, and forwards the request.
But the interception fails.
Exactly. If there is a slight protocol mismatch, or the proxy daemon crashes, the proxy fails to intercept the string, it blindly forwards the unmodified request to the backend provider.
In the authentication server, receives an API request where the bearer token is literally just the word POXY managed.
Right. The server hashes it, finds no match, and instantly throws a 401 unauthorized error. Meanwhile, you, the developer, are sitting there staring at your terminal. You know your credit card is valid, you know your API key is correct, but you are getting a 401 error because you don't realize the proxy swallowed your key.
That is infuriating because the error message points you in the completely wrong direction. You think it's a billing issue, but it's a routing issue. What about streaming failures? The sources mentioned SSE issues quite a bit.
Streaming relies on server-sent events, or SSE. It is a very delicate TCP connection. The model doesn't generate the whole script and send it at once. It streams the response back chunk by chunk.
So there's a constant trickle of data.
Yes. Every time you add an extra proxy layer, you add a potential bottleneck. If an intermediate proxy has a strict 30-second read timeout, and the LLM takes 35 seconds to ponder a complex problem before streaming the next chunk, the proxy will abruptly terminate the socket.
You essentially hung up the phone while the model was still talking. What about tool call mismatches? How does a proxy break a tool call?
Imagine you're using Codex, and it decides it needs to execute a web search. It constructs a complex web_search JSON object. But let's say you used CC Switch to route that specific request to a local instance of Llama 3 running on your own hardware.
A local quantized model.
Right. Smaller, local models often only accept strict text generation. They lack the sophisticated parsing required to handle arbitrary tool types. If Codex sends a web search request and your local proxy fails to filter it gracefully, the local model's parser will choke on the unexpected JSON schema and crash.
It returns a 400 bad request error. The proxy creates a blind spot where advanced capabilities are assumed, but physically not supported. What about billing?
Billing confusion is a massive liability. If the proxy hides the real provider route from you, diagnosing token usage becomes impossible. If you suddenly get a 429 rate limit exceeded error, you have no context.
Right, you don't know who is throttling you.
Exactly. When the proxy abstracts the route, you lose all visibility into the invoice.
And the final con listed. Stale model catalogs.
A local proxy GUI relies on a hard-coded or cached catalog of available models. When a new model drops overnight, the official endpoint knows instantly. But if your local CC Switch hasn't updated its catalog, that new model is completely invisible to you.
So synthesizing all of this, what is the golden rule for CC Switch? How do we summarize when it is actually appropriate to use this thing?
CC Switch is a highly useful tool, but only under strict conditions. It is worth adding only when the active route, the model, the cost, the errors, and the rollback state are completely inspectable by you. If it acts as a black box where you cannot tell where your request is going, turn it off.
Turn it off. It's just not worth a debugging nightmare. Okay, let's say a listener didn't turn it off, or they simply misconfigured a native setting and now their terminal is throwing errors. It is time for troubleshooting. Let's walk through the error matrix.
We should start with the most common and often most misleading error: model not found.
I have spent hours on this one. You type in the model name exactly as you think it should be, and the API just rejects it.
This usually stems from a catalog mismatch. You might be asking for a model alias that the specific proxy doesn't recognize because they require the exact version string.
Like putting in a short name instead of the date-stamped one.
Right. The fix is never to guess aliases. You must inspect the selected model string in your configuration, check the provider docs, and manually input the confirmed model string.
Next on the matrix, 401 or 403 authentication errors.
We explored the mechanics of this with the PRXY managed bug. A 401 means you are completely unauthenticated. A 403 means you are authenticated but forbidden from accessing the resource.
Like trying to use a free tier API key to access a premium enterprise model?
Exactly. To fix this, bypass the proxy entirely. Restore the least privileged valid key directly into a native configuration, establish a direct line to the provider until it succeeds, and then slowly add the complexity back.
Okay, here is one that trips up so many people.
Yeah.
The 404 base URL error. I always assumed a 404 just meant the server was down.
A 404 explicitly means the requested endpoint path was not found on the server. The server is up, but you knocked on the wrong door. In these workflows, 99% of the time, this is caused by missing the /v1 suffix at the end of the endpoint URL.
Explain how that missing suffix caused the 404.
If the documentation says a base URL is a p.example.com and you put that in your config, Codex might append /chat/completions to it, but the server is configured to only listen on /v1/chat/completions.
Oh, so the router doesn't match the path, and it throws a 404. The fix is simply ensuring the path includes the correct API versioning suffix.
Yes. Then there is the massive protocol clash we discussed earlier, responses API versus chat completions.
Right. Codex is sending rich JSON payloads meant for responses, and the endpoint expects simple message arrays. They cannot communicate.
The fix is architectural. Either route to a provider that natively supports responses, or insert a translation layer like OpenCodex that converts the payload accurately.
We also talked about streaming and SSE stalls where the terminal just hangs.
The TCP timeouts. The
Yeah.
fix is ruthless. Remove the bad proxy layer. Connect directly to the provider. If it works, the proxy service itself is dropping the connection.
What about context limits? The matrix lists context limit mismatch. Why does this happen silently?
This is a fascinating failure related to tokenizers. You are using a proxy route that points to an older model with an 8,192 token limit. But your coding agent uses a different tokenizer to estimate the size, thinks it's small enough, and sends 10,000 tokens.
The model just chokes on it.
It rejects the payload entirely. You have to ensure the destination model supports the context window your agent is configured to send.
Next is quota and rate limits.
HTTP 429 errors. Too many requests. The fix is simple: wait it out or route your traffic to an authorized, paid alternative.
And double proxy loops. That sounds terrifying.
It is request chain-based URL recursion. Imagine you point CC Switch to route its traffic through OpenCodex, but you accidentally left an old configuration in OpenCodex that routes its traffic back to CC Switch.
Oh my God, the power strips are plugged into each other in a circle.
Exactly. You fire one request and it bounces back and forth infinitely until the system crashes. You fix it by aggressively removing layers and drawing a straight line from the client to the provider.
We also have wrong provider billing.
A token accounting failure. You think you are hitting a cheap local model, but your proxy's routing table is misconfigured and silently routing to a premium API. You must isolate the billing route and label your profiles with absolute clarity.
And finally, the concurrency nightmare. Two agents editing the same files.
Overwritten work. The fix is implementing the single writer rule using separate Git work trees. Never let two AI tools write to the same directory simultaneously.
So we know the errors. We know why they happen. Now let's talk about behavior. Imagine you are staring at your terminal. You just fired off a massive refactoring request. The system stalls and then throws a massive block of red error text. My human instinct is to just hit the up arrow and mash enter. I just want to retry it.
Which is the absolute worst thing you can do in an agentic workflow.
Right, because if you blindly retry, you might execute a partial tool call. You're essentially rolling the dice with your code base. If it failed halfway through writing a file, retrying might append the same code twice.
Exactly. You need a disciplined approach to reestablishing trust. We call this the recovery ladder. It is a step-by-step execution protocol for when things break.
Walk us up the ladder. Step 1.
Freeze duplicate submissions immediately. Stop hitting retry. Take your hands off the keyboard.
Step 2.
Identify the failing layer. Do not guess. Look at the raw error logs. Pinpoint the exact node that threw the error.
Step 3.
Restore the last known good profile. Go back to a configuration that you know unequivocally worked yesterday. Strip away the complexity.
Step 4. And this feels like the most critical one.
Run exactly one read-only query. Do not ask the model to write code. Ask it something trivial that isolates state, like, what is the capital of France? Or read this specific function and explain it without modifying it.
Why do we do this? What does asking about the capital of France prove?
It proves that the network path, the authentication headers, and the basic HTTP protocol are functioning correctly. It isolates the network from the file system. Do not proceed to write operations until this succeeds.
Step 5.
Run one minimal tool call. Ask it to list the contents of a directory. Verify that the model understands how to format its tools over this specific route.
Step 6.
Perform one isolated write in a safe environment. Have it create a dummy file in a test folder, or better yet, in a separate Git work tree.
Step 7.
Run your test suite. Ensure that the dummy file insertion didn't break the build environment.
And finally, Step 8.
Only after climbing those rungs do you resume normal work. You have systematically proven that everything is functional.
There's a crucial rule here at the very end of the ladder regarding idempotency. If you had a task that was accepted or possibly accepted right as the system crashed, what do? Because you don't know if the file was actually saved.
This is a classic network partition problem. You must read back those tasks before resubmission. If your local network dropped before you received the 200 OK confirmation, you must manually inspect the file. Did the change apply?
Because if you blindly resubmit without checking, you might duplicate the code insertion.
Yes. Read before you write. Always verify state.
That is a masterclass in debugging. It turns panic into a structured diagnostic process. All right, as we wrap up, we need to segment our recommendations. Let's outline the path for beginners.
If you are a beginner or you just want a reliable environment, your path is simple. Stick to the Codex native provider configuration first.
Yes. Do not install a bunch of extra managers. Don't download CC Switch on day one. Use one provider. Configure one profile natively. Ensure a read-only request works before you do anything else. Do not introduce proxies.
The fewer moving parts you have, the fewer things that can break silently. Every proxy is a potential failure point. But we have to acknowledge the advanced users.
Right, the power users, the people who genuinely need to jump between Anthropic, OpenAI, and local models dynamically.
For advanced users, it is architecturally acceptable to add one OpenAI-compatible router. That might be OpenCodex for translation or CC Switch for profile management, but there is a massive caveat.
What is the caveat?
This must only be done after rigorous readback tests confirm that the protocol translation, the streaming behavior, and the tool call formatting are functioning flawlessly. You test the edges of the capability.
Which brings us to the anti-stacking rule. We both need to emphasize this. Do not recommend stacking multiple proxies by default.
It is the most common and destructive architectural mistake I see. People run CC Switch, which routes into OpenCodex, which routes into a local inference server, which then routes to the cloud. It is absurd. Only stack proxies if a verified use case clearly outweighs the massive failure surface it creates.
Do not plug the power strips into each other. Keep the signal path as short and observable as physically possible.
Exactly. Direct lines of communication are always superior.
This has been an incredibly dense mechanical deep dive into the architecture of multi-model workflows. We covered protocol clashes, file corruption, HTTP payloads, and how to physically recover a crashed workspace. I want to leave you, the listener, with exactly 3 highly specific takeaways to mull over today.
These are the core principles that will save you hours of debugging.
Takeaway 1. Start with the fewest layers that make Codex work. Do not stack proxies first.
Complexity is a tax on your time. Only pay it when you absolutely have to.
Takeaway 2. OpenCodex is strongest as an isolated reviewer or second opinion. Do not let two agents write the same files.
Enforce the single writer rule. Rely on Git work trees. Protect your active code base from concurrent automated edits at all costs.
Takeaway 3. CC Switch is worth adding only when route, model, cost, errors, and rollback are inspectable.
If the management tool obscures the reality of your API traffic, it is a liability, not an asset. Demand complete visibility from every layer of your stack.
If this helped you separate Codex, OpenCodex, and CC Switch safely, please like, subscribe to PyPI AI Everyday Lab, share it, and turn on notifications.